Look at a supercomputer or a high-powered laser grid. We construct these massive, complex systems because the macroscopic universe behaves with consistent logic. Objects occupy definite locations, and cause reliably leads to effect. But at the subatomic scale, that logic seems to vanish. Physicists in the 1930s realized that particles can seemingly occupy multiple states at once. Erwin Schrödinger famously challenged this with a thought experiment, where a cat in a box is considered simultaneously alive and dead until the box is opened, a scenario that contradicts our physical experience. For decades, the standard response has been to build increasingly dense mathematical models. We have stacked equation upon equation to force the universe to make sense within our physical laws. A different approach, rooted in the philosophy of convivial solipsism, suggests these paradoxes might not exist in the physical universe at all. Instead, they may be artifacts of how the human mind processes data. Under this theory, the focus of physics moves from measuring the world as it is to defining exactly what an observer is capable of knowing about it. Imagine an observer trying to measure a single particle. To get a clear result, they have to ignore a near-infinite amount of surrounding data. Helen calls this a maximal accessible variable, a measurable trait like particle spin. But zooming out, this point is surrounded by a matrix of inaccessible variables: the particle's true state, a total amount of information the human mind mathematically cannot process simultaneously. This creates the central tension of the Bell experiment. We observe two entangled particles separated by a vast distance of empty space. Measuring one seems to determine the state of the other instantly, violating our understanding of how information travels. This violation is captured by the CHSH inequality, a mathematical proof that entanglement shouldn't work this way. However, that proof requires an observer to model 4 different spin variables simultaneously. If the human mind is fundamentally limited to only 2 maximal variables at a time, the mathematical model used to prove the paradox becomes impossible for us to actually verify. In this framework, Schrödinger's cat represents a don't-know state. It marks the specific point where the observer's ability to access information ends. Because we cannot directly access the full state of the universe, physicists use advanced mathematics to theorize about what exists beyond our reach. String theory utilizes 11-dimensional supergeometry to account for these hidden factors, mathematically balancing fermions and bosons in a realm consistently beyond our perception. We see this same reliance on invisible scaffolding when we move to the cosmic scale to study the behavior of galaxies and gravity. Theories like F of Q gravity replace curved spacetime with a flat grid using the Levi-Civita connection. These connections act as mathematical scaffolding, allowing us to calculate gravitational effects our minds cannot visualize directly. While string theory and F of Q gravity address different scales, they both provide the tools to navigate the inaccessible. They allow us to build logical structures over the gaps where our direct observation fails. We continue to build massive infrastructure, from particle accelerators to deep space observatories, to test these mathematical structures. Whether we use Wilson loops in quantum gravity or Hilbert spaces in quantum foundations, the goal remains the same: finding a way to describe what we cannot see. Theoretical physics translates the inaccessible parts of the universe into the limited language of human logic. The unvarnished reality of the universe is still out there, existing independently of the mathematical scaffolding we use to understand it. The paradoxes of physics describe the edges of our current ability to process the universe. Exploring these limits is only the beginning. Drop a like and subscribe to stay tuned for our next deep dive, and let us know in the comments what you want to see next. This video was brought to you by Synestic Systems, founded by Shane Persinger.